Think like Tesla.
Think like Tesla, Micah here. Okay, here's the deal. So previously we've talked about the magnetic loop antenna, and of course we talked about Tesla coils. So just a super quick review here using the diagram we made earlier. Tesla coil has a small number of turns and a capacitor that makes a resonant circuit, and then on the secondary has a large number of turns and effectively a capacitor from the high voltage side here to ground. So the important thing is that the resonant frequency here and here are the same. So you have a large buildup of energy at a high frequency which discharges. We also talked about the magnetic loop antenna. In this case, the idea is to resonate on a particularly chosen frequency. So for that we have an adjustable capacitor here on the secondary, which is typically one loop, sometimes two, and the primary is typically one loop. The goal of this is to generate a radio signal that can transmit or receive. And the reason this works is because of electromagnetic induction. Anytime you have even a single wire, but the effect is magnified when you have a coil. So let's say anytime you have a coil of wire, could have a magnetic core or not, it doesn't matter. When a magnetic field changes across this coil, it will induce an electrical current, a flow, and when there's an electrical current in here, it will induce a magnetic field. So that's how this works. That's how transformers work. And in the case of this magnetic loop, a typical frequency might be on the 20 meter band for ham radio. That's around 14 megahertz, 14 million cycles per second. With some tuning, you could probably get it to the 7 meter band, or sorry, the 40 meter band, which is 7 megahertz, or maybe even lower. But what if we could make it work on a much, much lower frequency? We're talking megameter bands. Actually, we're talking 60 hertz line current. In the UK, you have 50 hertz. In the US, it's 60 hertz. What if we had a coil? All right, so this is roughly the scale. So here's our dude. And what if we had a large coil? This would be an air coil with a bunch of turns and wires coming off of it. The amount of 60 hertz signal just flying around in the air, especially inside a house, inside a lab like this, with LED lights and switched power supplies and all kinds of things hooked up, there's probably a significant amount of 60 hertz hash just flying around. So the large size of this coil means this has a lot of surface area, a lot of signal is going to get pulled through there, and that will turn in. The magnetic field is a sine wave, more or less, so it's constantly changing. So that satisfies the requirement of a changing magnetic field. So we will have, between these 2 points, a measurable current induced. So we'll have to figure out the exact parameters of the coil and the physical construction and all that good stuff. But the other thing then we can do is, if we put the right capacitance across here, that will make this into a resonant circuit. And by tuning the capacitor and maybe the coil, I suspect this coil at this size is going to be very susceptible to changes in inductance from the geometry of it. Wiggling it around, moving it, might not be a perfect circle. So the actual inductance might vary around a bit. But we can figure out exactly the right capacitance value to put on here to make this resonant at 60 hertz. Now, I suspect, we can put terminals here, I suspect this is potentially a dangerous thing to do. If you look at the back of large solar panels, they have warning. It says this circuit may be live and energized even if everything else is cut off. Right? And a solar panel, anytime there's light falling on it, is generating at least the potential to have a current. So you got to be careful with those wires coming off of those. Same thing here. Anytime this is just existing, anytime this is a resonant circuit, it's going to be picking up 60 hertz cycle. It's going to be building up energy in the tank circuit here, and there could be a substantial amount of electricity, maybe, we'll see, across these terminals. And there's no way to turn it off other than taking it apart, right? Disconnecting the capacitors. So there are capacitors. There's large value capacitors used for motor starting and things like that. We're gonna hook some of those up, and we're gonna make a large coil, and we are gonna see what happens with this. So before you try anything like this on your own, be sure and be aware of safety concerns. Be safe. This is potentially as dangerous as a line-powered circuit without being connected to the line mains at all. So be careful out there. I'll include the link to the safety video. And let's go take a look at this. I don't have the camera set up to do this nicely, so this is going to be a phone video without the crisp, clean audio of my Blue Yeti. But here we go. Let's take a look. Okay, here we go. If you're motion sick, you might want to fast forward this part, but look at this guy. Goes all the way up here. It's draped over my cabinet. And it comes all the way down here. And back around again. So this was RCA speaker wire. I picked up a 250-foot roll of it for pretty cheap on Amazon Warehouse. So let's see, how many loops do we get here? Okay, 14 loops. So it's actually a total of 28 turns if we hook them in series like I plan to. And yeah, what's the diameter of this thing? If it was a circle, it would probably be 6, 7, 8 feet. I guess I could do the math on that. And get the ends of it right here. Okay, so I'm going to try to not make you guys too motion sick here. I'm going to strip these wires. Alright, hang on, let me get my better wire stripper. So here's all the windings in series. So 28 turns, and we're getting about 2.3 millihenries, which is pretty good for an air core inductor. And if ESR is 3.2 ohms, which sounds about right for this amount of wire that we have in here, almost 500 feet. So let's go back to the workbench. 2.3, let's call it 2.35 millihenries. Okay, so we plug in 2.35 millihenries into the formula for resonant frequency, which is 1 over 2 pi square root of LC. And if you do the math, it ends up being right around 3,000 microfarads. That's a fair amount of capacitance. Since this needs to be non-polarized, this could potentially develop high voltages, a couple hundred volts across it. I can't just whack a Banggood or AliExpress capacitor across there. So I'm going to look around for this. The other thing I need to play around with, and this is just difficult because of the size of the coil, is how much does that 2.35 millihenry change by moving around? Draped over on the cabinet doors the way it is, it's not exactly circular. So maybe having increasing the surface area would improve the inductance, or at least change it. So that's some more experimenting I got to do. But on my current timeline, that means it's going to have to happen in the next video. So stay tuned for this. If you have any thoughts, suggestions, things you'd like to try with this, let me know. One other thing I just want to add while I'm thinking of it is, can this be used for energy harvesting? Well, in a strict technical sense, yes. But in an economic sense, I don't think so. Because I'm already paying for all this 60 cycle current that's floating in the air. So it's already gone through my electrical meter. Maybe I could drape a wire over the neighbor's house. And yeah, it's a joke, folks. All right, stay tuned. Subscribe for the details of this experiment. We'll see where we can go with this. All right, thanks a lot. Bye.